history, at least back then, was the idea that mass was quantized. It came in chunks, certain measurable quantities as small chunks, and what we call the atom. And that by imagining mass and matter as being chunky, we made huge advances in chemistry and our understanding of science. And he posited that, well, maybe energy is the same way. That if we consider energy to be chunky, in teeny chunks, kind of like the atom is really a teeny chunk of matter, this matches experiment. And this was basically an assertion with no previous, there's no theory that pointed that this might possibly be the case. And so he was instantly and immediately dogpiled on. Man, he was ripped apart in professional correspondence, in articles to professional journals. And what we saw was one of the biggest backpedalings in history of science, where he said, okay, maybe not the energy is not, only coming in chunks. It's the energy of the light that's emitted. It's only the energies of the atoms in the solid that are somehow restricted. Then once they're put in a solid, then you get this chunkiness of energies coming out. And then, even though he got dogpiled on for that, he then backpedaled and say, okay, it's just the light that's emitted that comes in chunks. And so he did further qualifications, backing away from his initial very bold assertion. But meanwhile, while he was getting dogpiled on and doing this scientific backpedal, in this country, he would have been called a patent lawyer, one of the most highly paid professional scientists. At least that's the situation here. Some of the highest paid professional scientists in this country are patent lawyers. A fellow by the name of Einstein. In Europe, the title of the job was patent clerk, but it was pretty much the same job. To keep track of current research and to judge whether or not patent applications were in violation of other patents and were worth considering if they were basically physically possible, like no perpetual motion stuff. We talked about that earlier. And he was in a position to see a wide range of information from lots of different areas of science. And he interjected himself and said, hey guys, there might be something to this. And his explanation relied on the photoelectric effect. And the photoelectric effect, you shine light, ultraviolet light, on a chunk of metal, out pop electrons. It was only a few decades earlier that we even realized that electrons even exist and are part of the atom. But if you shine light on metal, boom, out come electrons. And the wave theory of light, which was then applied to this, had some predictions. Because light, being viewed as an electromagnetic wave, it carries a certain amount of energy that's incident on its surface. The idea that the electrons clearly come from an atom, and so the amount of energy that any one atom gets is basically a fraction of whatever wave comes in and can be intercepted by something the size of an atom. So that's kind of the basis. And what that meant was that the energy in the classical theory, the energy of the electrons should increase with the light intensity. So basically the electrons should be popping out of the surface a lot faster with more kinetic energy if we increase the intensity of the light. Basically that increases the energy per second delivered to any given atom. And then the idea was that individual atoms would absorb that energy and then boom, it would transfer to an electron that would zing away. So the more intensity light, the more energy of light, the more energy we should see in the electrons being popped off. Also, at very, very low intensity or very, very low frequencies, basically low energy incident light, it would take a while for a whole atom to absorb enough energy to spit out an electron. So it was anticipated that there should be a time lag before we should start to see the first electrons pop off if the intensity and frequency were very, very low. And third, the energy of the electrons that are popped off should also increase with the frequency of the light, because higher frequency light has more energy. So these are the predictions of the classical wave theory. The problem is that was not matched by experiment. And this was something that people were puzzling about and trying to refine and test the boundaries of before even Planck explained black body radiation. And so the problems with experiment is that there was no dependence of the electron energy on the light intensity. So if you increase the light intensity and the energy in the incident beam by increasing the intensity, you didn't change the average kinetic energy of the electrons that are popped off. You just made more of them. Doubling the intensity only doubled the number of electrons, did nothing to the average energy that those electrons have when they were popped off. That's in contradiction to the wave theory. The energy of the electrons popping off only depended on the frequency of the light, the energy of the incident light. And you can have very, very low intensity light and have the same energy electrons popping off as you had with high energy. The only dependence on the energies of the electrons that were popped off was on the frequency of the light. And even at very, very low intensities, when they really jacked it down as low as they could go on their devices, as soon as they turned the light on, as far as they could tell, instantaneously, you had the first photoelectrons being popped off. No time lag whatsoever. The absorption of the energy was instantaneous, even at incredibly low intensities. This really bothered people. And then if you increase the intensity, as I said, all you did was increase the number of photoelectrons, had no effect on their energy, and there was a cutoff frequency. That no matter what the intensity was, even if it's this extreme, is if your frequency was below a certain amount, you would never get any photoelectrons, regardless of the intensity. You could have light with 1,000 times less energy producing lots of photoelectrons compared to something that was 1,000 times more intense producing no electrons, just at a lower frequency light. These were problems. And Einstein came along and said, well, gosh, maybe Planck had something right, because the whole idea of the energy of light coming in discrete packets, discrete chunks, like what Planck initially had proposed, would completely explain this. And he called these packets of light photons. And we now talk about photons a lot. And not just the cool torpedoes in Star Trek. And furthermore, not only did that idea of the light coming in particles, where it's not a wave incident transferring energy over a time period to something as large as an atom, it's a single photon interacting with a single bound electron in the atom. And so the energy absorption is instantaneous. As soon as you have photons, light hitting the surface, you could have a photon of the energy corresponding to that frequency, giving all of its energy to an electron, and boom, off it goes. So the idea of light being photons let's just write that down. Particles we call photons. And so each photon has an energy HF. And he was able to show that if this is the energy the photons are getting, well, actually he went about another way. What energy, if energy comes in packets, what must the energy of these photons be to explain the specific observed cutoff frequency? Basically, what's the minimum energy? And the energy of the electrons that they do come off, what is their kinetic energy? That changed with frequency of light. And he found that if you wanted to model what is observed by experiment, what had to be is that the energy of those photons, those particles, had to be proportional to the frequency of the light. And the constant of proportionality, in order to exactly match what was observed in the cutoff frequency and in the energy of the electrons that were emitted, that constant had to be Planck's constant, the 6.63 times 10 to the minus 34 joules. That's exactly what it had to be. Almost overnight, Planck was a hero. Though he was dogpiled on severely, it was acknowledged that, in fact, he did have it right. And Einstein was very, very convincing. Basically, once Einstein came up with this explanation and this reasoning and backed it up with experiment, that he didn't do, by the way. He was basically comparing experiments that other people have done, and not just one person, but the experiments of hundreds of scientists. He brought all that research together, that body of research, as well as all the research that had been done on observing black body spectrum, and saying, hey, look at this. This is all remarkably consistent, and it matches Planck's prediction. And so this was the first clue that, in fact, energy does come in chunks. It is quantized. And out of this comes what we call quantum theory. It's basically the coupling of the idea that not only does mass come in chunks, but energy does as well. Einstein got the Nobel Prize for his explanation of the photoelectric effect. He actually got several Nobel Prizes, but that was one of them. Actually, no, several things were mentioned in the Nobel Prize, and this is one of them. This is one of the big ones. But this gave rise to quantum mechanics and the idea that we can describe successfully light as being like a particle. Remember, the early models of light had that light behaved like a particle. And then we saw things like interference and diffraction that gave a lot more credence to the idea that light was a wave. And then folks started to ask, well, is light a particle or is it a wave? And it turned out that as far as they could tell, it depends on what sort of circumstances you're dealing with, which model provides a better description. And it was kind of hard. It's like fitting a round peg into a square hole, the idea of light behaving as a particle to give us interference and diffraction. But folks spent quite a bit of time on this. And it started to all come together in just a very short period of time. If light behaves like a particle, this is what got people to thinking. Maybe particles could behave like, well, like a wave. If something we thought was a wave is actually behaving like a particle, maybe particles might behave sort of like waves as well. And this is where wave mechanics, or what is now called quantum mechanics, comes from. But I'd like to do a little bit of a pause here and see how much of this was actually absorbed, and do a question or two. So, here's the question. Light from a particular source is incident on a piece of metal, and it doesn't produce any photoelectrons. So in order to produce photoelectrons, what must you do? Must you increase the light intensity? Must you increase the frequency of the light? Must you increase the wavelength of light? Increase the temperature of the metal? Or in fact, none of the above? Think about this for a moment, please. Okay, get your cards ready. Okay, go ahead and show me what you're thinking. Folks online, hit a letter for chat. I see A, B, C's. Yeah. Anything else?
No D's or E's.
No D's or E's. Okay.
Probably more so A's and B's.
Okay. So, can I get a volunteer to defend why A is correct and that we need to increase the intensity of the light? Somebody online, please unmute and speak up.
I was just thinking of how the theory predicts how energy of the electrons increases with light intensity. And I was just looking over my notes and I see the word intensity a lot, so that's what I went with.
Increasing the intensity should increase the energy in the light, and that should increase the chance of us getting photoelectrons. Okay, can I have a volunteer to defend B, please? Then we need to increase the frequency. Mr. Crosgrove?
So based off of the explanation in the equation given up there, E equals, I don't know what that symbol is.
H.
H, okay. Times F. It's given that the energy basically, or the intensity, is that constant number that Planck found that was then backed up by Einstein later on. To give us the total energy, the only other variable that you could change would be the frequency.
Okay, since the energy of light, particle of light, a photon, is a constant times the frequency, that's what the electrons are absorbing. So therefore, to increase the chance of getting electrons, we need to increase the photon energy or increase the frequency.
Yeah.
Okay, can I get a volunteer to defend C, please, that we need to increase the wavelength? Anyone? Okay, nobody chose D or E, and D and E are not correct. It's either A, B, or C. I'm going to still leave C as a possibility, but the question is what affects the possibility of getting getting an electron out with light. We know we can increase the energy by increasing both intensity and frequency. Which is it though? It's not both. Let's have some discussion.
Yeah, you mentioned that below a certain threshold, it doesn't matter what you do to the intensity, the amount will still stay the same, but if you have to increase the frequency to get a reaction. Once you get past that threshold, the increase in intensity will increase the amount of electrons produced.
We have a discussion on chat.
Please.
I like using the equation to solve this question. I might change my answer to B based on that reasoning.
And what else?
That was it.
Okay, folks, any other thoughts? Most welcome. Please share them soon.
We got one more.
Please read it.
There was mention of a cutoff frequency which described that no electron was emitted regardless of intensity.
Okay, we've had a few comments. Go ahead and show me what you're thinking now by holding up a card or hitting a letter on chat. Is there anything but a B showing up?
Nope, unanimous.
Okay, unanimous at B, which is the correct answer here.
That was a productive discussion.
Well, basically, if we have a single electron absorbing a single photon in order to be ejected, and the energy of that photon is proportional to the frequency, well, if you have a frequency that's too low, no matter how many photons are going to hit this thing, they're going to hit it one after another. The energy of the electron doesn't like rack up. It's either all or nothing. This is one thing we didn't talk about that's relevant here, in that you could have multiple photons hitting a single electron in an atom after a while. It's very, very unlikely, but once an electron absorbs energy from a photon, if that energy is not enough to eject it from the atom, it will very, very quickly transfer that energy to elsewhere inside the atom and even to other neighboring atoms before you've got a significant chance of having another photon interact with that same electron. So for that reason, you don't have atoms storing up energy like what was predicted in the wave theory. It's an all or nothing based on a single instantaneous interaction. And for that reason, the only way to get photoelectrons is to have photons of enough energy to kick out an electron, because the atoms and the electrons have no way of storing that energy. In fact, they dissipate it very, very rapidly. Okay, let's go on to the next question. This is actually a little bit tougher. Black and white photographic film, this is going kind of way back in time. It's more sensitive to blue light than red light. So if you see movies where people are developing film, they'll do it in what's called a dark room. And what light they have is a dull red color. There's a reason for that. It does not expose the film. So for this reason, which of these three statements is correct? Basically, what's consistent with this? A, there are more photons in 1 joule of red light than in 1 joule of blue light. Or B, there are more photons in 1 joule of blue light than in 1 joule of red light. Or C, we have the same number of photons in 1 joule of red light and 1 joule of blue light. Remember, the joule is the unit of energy.
Photons is short for photoelectrons, right?
Photons are particles of light. They are not electrons.
Okay.
Photons are what we call particles of light. And an electron in the photoelectric effect will absorb a photon, a particle of light, gaining energy. And if it gains enough energy from that photon, the electron could be ejected and become what we call a photoelectron.
Okay, that makes sense.
That is the phrasing.
Okay, I
So
understand.
joule is the unit of energy. And in fact, if you go into just about every country on the planet except for one, and you pick up a can of diet soda, it will say low joule cola. Because that's what the rest of the planet uses instead of calories. Joules. So think about this for a moment or two. Okay, folks, show me your cards or hit a letter on chat, please. I'm seeing A, B's, and C's.
Yeah.
Okay. Can I get a volunteer? Let's go in reverse order. Can I get a volunteer to define C, please? We have the same number of photons in a joule of red light and a joule of blue light. A volunteer for C, please. We had quite a few C's, didn't we?
Some. I've been trying to explain.
Mr. Anderson, please do.
So my reasoning with this is that we already established that the intensity doesn't make so much of a difference as the frequency, I think. And so my reasoning was, since it's the frequency that makes the bigger difference in the reaction, it doesn't really matter what the intensity is.
Okay, so the argument here is number of photons is intensity. Intensity of light is determined by the number of photons, and it's the frequency that's important, so number of photons shouldn't matter. It's not what's going on here at all, so we should have the same number of photons in a joule of blue light as opposed to a joule of red light. Did I sum that up?
Yeah, I think so.
Okay, can I get a volunteer to defend B? Do we have more photons in a joule of blue light than in a joule of red light?
I chose B just because with the photographic film being more sensitive to blue light than to red light, and the safe light in the photographer's dark rooms are red, makes me believe that there's more photons in 1 joule of blue light than in 1 joule of red light. And I also remember the star of the blue light being more powerful, higher intensity than the red.
Okay, so more photons means more likely to expose the film, and clearly that's what blue light is doing. It exposes it more than you would with red light, so there should be more photons in blue light.
Yep.
Can I get a volunteer to defend A? That there are more photons in a joule of red light than in a joule of blue light.
I'll go for it.
You do.
So I chose A, just as a guess. I heard you mention that this question was a little tricky. And when you were talking about photons and photographs, I just kind of thought maybe we needed more photons to produce a photograph. And so that's why I went with A.
Okay. Does anyone have anything to add to this discussion? Any of those points? Does anybody want to add something to?
We did have another discussion for C.
Please.
I just thought that the energy amount would not differ, but the wavelength of light varies.
Okay, there is a difference in wavelength between red light and blue light. That is true. Anyone else want to weigh in on this, on one of these points or the other?
I could give another reason for B.
Please do.
So when I was thinking of the color blue, it has a shorter wavelength and a higher frequency. And when you plug it into that equation, that E equals HF, I just thought that would kind of produce a higher number.
Okay, so a photon of blue light has more energy because E equals HF increases with frequency.
Yeah.
And so if we had more energy in a blue photon than a red one, how does that support B?
I just figured there would be more photons with more energy. That was my guess.
Okay, but it is correct that a photon of blue light will carry more energy than a photon of red light because of the E equals HF. Okay, we've had some discussion. We've had some defenses. Go ahead and show me your cards, what you're thinking, A, B, or C. What's it looking like?
Unanimous B on chat.
Wow. That's actually kind of surprising. B is the correct answer. No, wait, no. Did I get it wrong? No, B is the wrong answer. Dang it. A is the correct answer here. For the reason that was kind of stated for the last, I think it was Mr. Horsley that spoke up. For an individual photon, since the energy of that photon is given by Planck's constant times the frequency, the higher frequency of light, the photons in that light have more energy. Does that make sense? And whether or not a photographic film is exposed is, well, the photons have to have enough energy to cause that chemical reaction. If you have lots and lots of low energy photons, it's not going to expose the film because any one photon doesn't pack enough punch to cause that chemical reaction. But if you've got a photon of enough energy, it will cause a reaction. And so the blue light has enough energy to cause that reaction. That means the energy the blue photons carry is greater. And if you have a fixed amount of energy, you're going to have fewer photons if they're a high energy.
So they're
Does that make sense?
photons, but they're more effective because they carry more of the energy. They're
Okay.
more energy densities.
It's like this. Marbles don't have as much mass as a billiard ball, right? So comparing mass, the blue photons are like the billiard balls. The red photons are like the marbles. And let's say we have 10 pounds of either marbles or billiard balls. How many billiard balls are there in 10 pounds as opposed to how many marbles are there in 10 pounds? Which do you think you have more of? More marbles in 10 pounds or more billiard balls in 10 pounds?
Okay, that makes sense.
That's what we're getting at here. Each individual photon has more energy if it's a higher frequency. And so if you're talking about a fixed amount of energy, you won't need as many blue photons to get to 1 joule. You'll need a whole bunch more photons to get to a joule of red light. Because individually, the red photons don't have enough energy to cause that chemical reaction, but a blue photon does. That's what's going on here. The more energy for any given photon, the more frequency. The higher the frequency, the more energy each photon has. Okay, I forgot, what was my next question? Okay, let's hold off on that. Actually, I could probably just erase what I have up here. Okay, after this very startling idea that light behaves like a particle, something we thought had a wave, hands down, wave behavior actually has particle-like behavior, led some to posit the idea that maybe particles have wave-like behavior. And there were several people kind of mulling around with this idea in scientific correspondence. But de Broglie gets the credit for at least making the first formal proposal, in that this is something he spent a lot of time thinking about. He has extensive notes. His journals were packed with calculations for months prior to a large gathering of physicists. And de Broglie was, he was a character. So instead of presenting his body of work at a formal talk, he decided after the second day of the conference, when a bunch of the physicists were gathered at a bar and well liquored up, he whipped out a napkin and said, guys, I've been thinking, what if, particles have a wavelength? Yeah. And the way he argued it was that, well, we know that light carries momentum. And so we can use that idea to think of what sort of momentum you'd get for a certain wavelength. Well, let's turn that around and take the momentum of a particle to figure out what wavelength it would have. And he did a quick back of the envelope sketch basically on a napkin in that restaurant and said, well, gosh, that would mean an electron could have these wavelengths. And if we were restricted to say what we think we know that electrons have in the atom, this is jumping ahead to another chapter. But the first models of the atom had that, Bohr proposed this, that the energy levels in an atom were discrete. And that we only had light emitted when electrons could change from one energy level to another. But why we had those specific energy levels was a mystery to people. But Bohr was able to explain the model of the atom exactly by saying, by proposing this idea. What de Broglie did on this napkin was say, well, gosh, let's look at the Bohr model of the atom, that Bohr was just talking about today. If we think of the electrons as having a wavelength, hey, look, these Bohr orbit radii that Bohr came up with would correspond to standing waves of the electrons of that wavelength. Where imagine having a wavelength going around in an orbit like this, because that was the idea that Bohr had, that you had electrons in like circular orbits, which turned out to be wrong, but was a sort of successful model. And he said, look, we get the same orbits and the same energies differences that Bohr predicted if we just think of the electron as having a wavelength corresponding to the momentum it would have. And the fact that he'd been working on these calculations for months, backing them over and over again with very careful stuff and reasoning, and that he just, instead of doing it in a talk, just spewed it out on a napkin to a couple of physicists, basically to impress them on how brilliant he was, when really it's something he'd been spending months thinking about. That was de Broglie. Just thought I'd share a little bit of a personality story to you. I don't know if that's of interest, but so it turns out that this description worked remarkably well and filled in a lot of gaps and had to be refined considerably, but the fact that it helped explain a bit of phenomena early on meant that there was an element of reality to it, an element of truth. And a fellow by the name of Heisenberg took this one step farther. And well, in waves, we have, if you basically put the math together, like what we have with electric fields and magnetic fields and waves, but also with like water waves, pretty much any other wave we could describe, sound waves, you could develop what's called a wave equation that you could use to predict what the intensity of the wave would be, how that wave would propagate, how it would react. And he took de Broglie's wavelength idea and then wrote a wave equation for particles. And it was this that not only explained Bohr's model of the atom, but went one way farther, because there's a lot of things that Bohr's model did not describe well at all. But a complete mathematical description of the electrons as if they are waves or have wave-like behavior gave an even better description of the atom than what Bohr came up with. And we'll talk about this again later. But underlying all of this is that there is a waviness to things with mass. And where this was going and where quantum mechanics or wave mechanics eventually evolved to is not that particles are so much waves, though we can describe them as waves and with wave equations, but there seemed to be an underlying principle that Heisenberg seized on, and we now call the Heisenberg uncertainty principle. Well, I had to write down the Broglie wavelength. De Broglie's idea is that the wavelength of a particle is equal to this Planck's constant again. It keeps showing up, divided by the momentum of that particle. Then if you make this assumption, and this is not just an assumption, this is actually a calculation, because this goes the other way around, by looking at the momentum light has for a certain wavelength, but turning that around to looking at the wavelength the particle would have. It turns out to have the same relationship here. It comes again between the relationship between energy and momentum and the relationship with energy of a photon. This Planck's constant comes up. But actually, we're getting really short on time. I don't have enough time to get into the uncertainty principle just yet, but basically what de Broglie was predicting is that we should see interference and diffraction effects from particles. And it's actually quite a testament to the success of this theory that because of other things that this theory predicted, this wave mechanics, this quantum mechanics, people are pretty much convinced that this would be true, but even though they didn't have the technology to actually do diffraction and interference with particles. And it wasn't until several decades later that we actually saw diffraction and interference patterns with electrons and even ions. But we now do. We can send electrons through thin slits one at a time. And their intensity over time will build up these interference patterns. It's not in the, well, this is actually pretty darn profound. And this then is probably a good segue into the uncertainty principle. We'll talk more about this then tomorrow. Thank you for your attention.